everybody. So this is trial number 3 on making this video. Hopefully it works out. So I'll try and be quick about it. All right. So we're trying to generate a summation of how much force is being exerted on a wall that's like in a pool kind of thing. In order to get there, we have to talk about pressure. And pressure per unit is by definition force divided by unit area, and we need to keep that in mind when we're trying to work through all of the development of this. So pressure in water is referred to as hydrostatic pressure, and hydrostatic pressure has the property that it has the same magnitude in all directions. We are assuming standing water, right? Not flowing water. Specifically, the hydrostatic pressure on a vertical wall of a swimming pool at a depth of h is the density times the gravity times the height. The question is why or how? Well, let's go back for a second and let's talk about the idea of force. Force is just mass times acceleration. Well, in the world of water, how do we generate mass? Well, in order to generate mass, we have to have volume and density. Now, the acceleration is the gravity part. Okay, so we'll have gravity traveling there and there. But volume, well, the way we get volume is we take the area of the base and then we multiply it by its height. And then to make it mass, we multiply it by density. So the force descriptor is the area times the height times the density times the gravity. To get us to talk about pressure per unit, we need to divide by force by area. So if we write it out, we have area times height times density times gravity divided by area. And we have a cancellation going on there. And so pressure is really height times the density times the gravity. So the farther down you go, the more pressure you're going to feel. All right. So in order to capture that, we have to think about a couple of things. So the first thing is we want to have our y-axis pointing upwards, and we want to have y equaling 0 be the base. So we want to have 0 be the bottom of our figure. We're going to slice our shape horizontally into n strips, and delta y will be the width of our strips, which means we have y sub k minus 1 to y sub k, and y sub k star is the point in that special interval. So the height of the strip that we're going to look at is going to be a, which is the top of the figure, minus y sub k. And by setting it equal to 0, that becomes a fairly formulaic a rule. So the hydrostatic pressure, based on what we discovered over here, is just going to be the density times the gravity times the height, which is a minus y sub k star. Now the trick becomes finding the width of the strips. So we're going to always have to work to try and find that formula. Okay, and I'm circling here, but I really should be circling here, because you're going to get the width, and then you're going to multiply it by its height, and that's going to give you the area of the strip. And you're going to take the area of the strip, and you're going to multiply that by the pressure on the strip. Okay, and so that is our, we take a summation, put it there, and we tack on our limit, then we get to say it's equal to this thing. Turn the page, and just as an example, we're going to talk about pressure of water on a dam, and we have a trapezoidal figure. It's 30 meters high, it's 40 meters across, and 20 meters across on the bottom. Remember, I said to set the bottom of the figure at 0, so there's our 0. So that's going to go from negative 10 to 10, and it's going to go from negative 20 to 20. Using these 2 points, I derived the equation of that line, and this x is the width, but I need 2x for the total width. So I'm going to solve this equation. I'm going to get this equation. You can look at the numbers there, but you get y is equal to 3x plus negative 30. I'm going to solve for x, so I'm going to have x is equal to 1/3 times the quantity y plus 30 I'm going to have to double that, so now I'm going to have 2/3 y plus 30. Now, my density times my gravity is 9,800. We're going from 0 to 30. Here's our height, 30 minus y. Here's our width, 2/3 y plus 30. And here's the height of the strip, which is dy. And then I just pulled the numbers out, did some multiplication, and then I took the antiderivative, and I went from 0 to 30. I actually punched this into the calculator, and I'm somewhere around 1.18 times 10 to the 8th. I did want to make a comment about the units. So I wanted to show you how we end up with joules. So 1 Newton is equal to 1 kilogram times meters per second squared. Times meters per second squared. And I was trying to figure out where the joule comes in, or the Newton comes in. And so I started monkeying around with the way the units look. So the density is kilograms per meters cubed. The gravity is meters per second squared. The height is a meter, the width is a meter, and dy is a meter. So those three meters multiplied together will cancel that meter cubed out. So that's how we end up with kilograms times meter per second squared. Hopefully that helps a little bit.